Okay. Okay, great. Yeah, so as Kate said, I'm Rob Ricci. I am leading the CloubLab project, which is being built as a collaboration by 6 different institutions, led by the University of Utah. And I probably don't need to tell anybody in this room this, but the idea of the cloud is changing the way that we look at a lot of problems, right? So it raises a lot of interesting problems in computer science, but one of the very exciting things about it is that it has a lot of impacts that go, beyond, computer science and the areas that a lot of us work in out into the larger world. But it's still a pretty young and fast evolving area. So there's still a lot that we don't know in terms of, in terms of what its limits and what its fundamental properties are. So both from the perspective of researchers, by which I mean people who are, who will transform the cloud by doing, the research that drives it forward, as well as by what I might call users, who are people who are going to use the cloud and the results of that research to actually transform their own fields. But in order to do work in this area, we need to be able to run experiments at scale, and so in order to do this, we need flexible scientific infrastructure, and we need infrastructure that allows us to do work on fundamental science in the cloud. And I also believe that it's important that this research, that this infrastructure be built by and for the community that's going to be using it to make sure that it's responsive to that community's needs. And this workshop today is a big part of that. So something that I want to get out of the way early in this talk is to describe is to say that CloubLab is not a cloud, right? So CloubLab is actually a facility for researchers to come and build their own clouds. So if you think of the things that are a given, if you were to go use a commercial cloud, or if you were to go use a private cloud in your institution, things like the cloud management software, the virtualization layer, the networking layer, the storage stack. The point is to let you build and experiment with that stuff yourself, so that so that you can try to actually push that forward rather than using what is given to you by somebody else. So the basic vision here is that CloubLab is a kind of a meta cloud. It's a cloud for building clouds. We have a set of hardware resources that I'll describe in just a minute, and researchers come and build their own clouds on that. It is agnostic to specific cloud software, you can run existing cloud software stacks, things like things at the kind of cloud management level, like OpenStack, or maybe higher level frameworks like Hadoop, or you can take those and you can tweak them in some way and replace subsystems, make modifications to them, or build something all the way from the ground up, because you have control and visibility all the way down to the bare metal of the system, over all aspects of it. It's sliceable, so we can have multiple experiments that are running at the same time. We provide a pretty good deal of physical isolation in isolation in the performance sense between them, so that you don't have to be worrying about whether or not you're seeing artifacts from other simultaneous experiments. And one of the ways that I like to think about this is that one of the reasons that that the cloud has been transformative in a lot of areas is that it takes something that used to be quite difficult and time-consuming to obtain, and makes it as easy as filling out a form on a web page to get as many virtual servers as you can pay for. And that really inspires people to kind of think of new things that they can do with those. And our goal here is to make it just as easy to get your own entire cloud as it is to go to a cloud and get a virtual machine today. And I'll show you actually later in the talk what that looks like. So I have a couple slides here on the research enabled, but I'm not going to spend a lot of time on them because that's really what this workshop is about. But I do want to kind of drive home the point that we expect to support two kind of classes of research. One is research on cloud architectures, where you want to modify or need to do inspection or whatever of kind of the software that we consider, as being the software that defines and builds the cloud, as well as enabling new applications that maybe don't work particularly well on today's cloud, but if you could change the architecture of the cloud, you might be able to do a better job of running things like real-time systems or systems with strong security and privacy guarantees. So we expect to support both those classes of applications. So what is CloubLab? So it's this facility that we're building for transformative cloud research. The underpinnings of it are the Emulab and Genie software that my group has developed for about 15 years now. And as I said, you get control and visibility all the way down to the bare metal. And this is important for being able to do repeatable and scientific experiments, because if you're using another system where you don't have visibility into perhaps what the actual hardware details of that system are, or what else you might be sharing with at the same time, it's very hard to establish ground truth and to tease out what things that you're measuring are fundamental and what are properties of the system that you're using. We're going to provide a diverse set of resources that are distributed across a couple of sites. So in phase 1, we are building clusters at the University of Utah, University of Wisconsin, and Clemson University. And these will be interconnected using existing network resources from our campuses, from our regionals, and Internet 2's AL2S network, which gives us a nationwide SDN to interconnect them. And it will also be federated with the Genie testbed that Susie and Keith mentioned, so that you'll be able to run experiments that use individual clusters in the system, or potentially run across many different sites and incorporate a broad diversity of resources. So as I said, we're building this on top of the Emulab platform. It's many of you in this room have used Emulab in the past. Another set of you have used our contribution to the Genie project, which is called ProtoGenie. The InstaGenie racks run the software. There are actually a number of other test beds, including the probe test bed, that use the same software stack to manage the test bed as well. So it's something we've been building for a long time. We've been working on it since 1999, and it's served a lot of users. And the basic idea is we provision machines at a bare metal level and then get out of the way. It has some runtime services, but you can mostly ignore them if you want. So that you can have complete control over the physical machines that we allocate to you, which is important if you want to be able to then create your own virtual machines on them. It has a web. We have a web interface. I'm actually going to show you what the web interface for CloubLab looks like briefly later in this talk. But I also want to mention that it has a very rich set of APIs that have come out of the Genie project, so you can kind of directly write programs against it to allocate resources, manage them, and so forth. Another aspect of it that I really want to highlight is, we view this as, really that it needs to meet, we're not looking here at things like SLAs, et cetera, right? The bar we have is somewhat higher in the sense that we need to build something that meets the bar of a scientific instrument, right? So when you run experiments on it, you should be pretty confident that you're measuring what you think you are, and not artifacts of the platform that you're running on, or artifacts of simultaneous use. So we provide physical isolation for most resources. So when we allocate a physical machine to you, it's yours. Nobody else is using it. We can allocate entire physical disks and entire physical switches. And another aspect of building something that's a scientific instrument for repeatable research is that CloubLab is built around this idea we call profiles. So a profile is something that captures everything that you need to run an experiment. So it captures the software and the data that you use, but it also provides a detailed description of the hardware that you ran that experiment on, so that you can share this profile with somebody else. And your collaborators, or you can put this in a publication, and you can say, look, here is how to get the exact environment in which I ran this experiment. So as I said, we're building 3 different clusters in the first phase. It's one facility though, one account gets you access to all of them. You can run experiments that cross all of these different resources at the same time. But what we've done is each of the 3 places that we're building a cluster has partnered with a different hardware vendor that we have a close relationship with. So we took we came up with kind of a reference design, and then each of these 3 facilities has a different kind of take on that design. So we're shooting for about 5,000 cores per site for a total of 15,000 cores. 10 gig networking to everything, software-defined networking within all of those clusters, and then because they're all connected to Internet 2's L2S platform, you can get software-defined networking between them as well. And so we're going to spend the next little part of my talk. I'll talk about the cluster from the University of Utah, which we're partnering with HP to look at power efficient stuff, and then I'll have Aditya come and talk about the cluster they're building at Wisconsin, and KC will come and talk about the cluster that they're building at Clemson. Before I go into talking about the specifics of the hardware, just to give you a sense of the schedule, so we're getting half of the hardware in the first year of the grant. Some of it's already showed up, some of it's on its way, and then in the future years, we'll be doing refreshes to kind of build it up to its full size. So most of what you're going to hear described is like the first half. So the cluster that the University of Utah is building with HP is up, it's alive, it has blinky lights. And it looks kind of small, but this is actually very deceiving because it's incredibly dense. So the boxes that you see in there are these boxes from HP that they call Moonshot. So this is about a 4 rack unit box. It has these cartridges in it, of which there are 45. Each of these is an independent server. And we're building this cluster with the theme of power efficiency. So these are all 60 ARM processors. They're quite nice. They have 8 cores running at 2.4 gigahertz. So these are not wimpy ARM machines. They have 120 gigs of flash memory and 64 gigs of RAM. So they're really quite capable as servers, but also coming in at a fraction of the power consumption of an x86 machine. And we're going to have instrumentation on here so that you can actually get the power readings for machines that you're using, so you can actually evaluate their power performance kind of trade-offs. These chassis also have 2 switches in them. These switches run OpenFlow 1.3, and we actually have OpenFlow 1.3 throughout the network that we've built at the University of Utah. So we have 7 of these chassis. So in the first half of our buy, we have 315 nodes. Those 2 sparse racks have 315 servers in them, with about 2,500 cores and almost 10 terabits of network switching. They're connected to, so each of those chassis has 320 gigs of uplink to a big core switch that's has full internal bisection bandwidth. And when we buy the second half of the phase 1 cluster, those will go directly into that core. So we have this very large set. We have some pretty large sets of areas with full bisection bandwidth in them. So this cluster will be suitable for experiments that want to explore power performance trade-offs, that want instrumentation of power and other environmental values like temperature sensors, et cetera. And then because we're getting these cheaper ARM cores, we have a whole lot of machines in cores. So this is a good cluster if you need lots of those things. I actually want to tell a story about this next bullet point. So I put this bullet point about RDMA and Rocky on my slides a couple of days ago, and then yesterday, as I was sitting in the airport in Salt Lake waiting to come here, I actually had a user email us and ask, oh, does anybody know how to set this up on our machines? And by the time I'd gotten off the plane, he had like figured it out and sent this big, you know, multi-page set of instructions to our user list. So this is a real thing that people are using. It's also good for, we have the ability to do out-of-band provisioning on these switches. So we can't do this yet, but one of the features that we're going to develop is the ability to give somebody an entire chassis and actually give them like administrative control over the switch. So if you actually want, switches that you temporarily own, we'll be able to do that on this cluster. As I said, we'll have OpenFlow 1.3 throughout it. Also, through our relationship with HP, we actually have contacts at Applied Micro, who are the folks that make the ARM system on chip that we're using here, who have expressed an interest in working with people who want to kind of have the hardware engineers to talk to get their workloads up and running, efficiently on these things. So if you're interested in actually working with the people who designed the system on chip here, talk to me and we'll make that connection. Also, we've recently HP has also let us know that they have an FPGA platform for this that they're interested in having researchers try out. So people who want to use FPGAs for various kinds of acceleration or power efficient systems. So also let me know if you are interested in that, and we'll put you in touch with the people at HP who can help you with that. And then Aditya, do you want to go ahead and talk about the cluster from Wisconsin? Oh yeah, of course.
Can people hear me in the back? So hi everyone, I'm Aditya Akela from the University of Wisconsin-Madison, and I'm here to tell you about the Wisconsin CloubLab cluster. We are building this in close collaboration with Cisco Systems, and the compute infrastructure, storage, and the networking interconnect we have designed and we plan to deploy in this cluster is meant to closely reflect some of the most modern commercial data centers out there. In that spirit, our cluster is built in sort of a hierarchical fashion. At the very bottom, we have about 12 racks of compute servers. Each rack has 20 servers, and each server has dual 10 gig uplink to a top of the rack switch, sort of like a mini scale large data center. Each top of the rack switch is a Cisco Nexus 3172PQ switch, and I'm going to talk about the specific features of this switch in a little bit. Each switch has a 40 gig uplink to every one of 6 spine layer switches. So a total of 240 gigs going out of the top of the rack switch up to the spine layer. And each spine layer switch is a different Cisco Nexus 3000 series switch, specifically 3132Q. And essentially, this gives you a very high bisection bandwidth interconnect, and it topology, which is kind of what the centers in Google and Azure essentially look like today. The spine layer switches are connected to a single core switch using 40 gigabit second links. The core switch, again, one of the switches we have been using for our top of the rack switches, namely Nexus 3172PQ. So this is what the cluster or the mini data center looks like. The core switch is connected to the rest of the campus using a total of 80 gigabit per second of bandwidth. And this is essentially the total amount of bandwidth we have to move data and stuff into and out of our cluster. And we are connected I2 to the rest of the internet, internet 2 to the rest of the internet. So unlike the Utah cluster, which is alive and breathing, we are not quite there yet. We ordered the system, and I think it got shipped, and it's somewhere in the middle of the United States. It's going to show up next week, or maybe in 10 days' time, and it should be up and running sometime in early spring. So let me go into some more details of the the individual pieces of the infrastructure, the compute, storage, and networking. Let me start with the compute servers and the storage that we have provisioned in them. Like Rob mentioned, we're going to build this in two phases, in phase 1 and phase 2. This is mainly driven by how we are getting funding from NSF. In the first phase, you recall we had 12 cluster racks, each having 20 servers, so that's a total of 240 servers. In the first stage, we're going to provision 100 of these 240 servers. These 100 servers are going to be of two different kinds. 90 of these servers will be Cisco's C220 series servers with the M4 chassis. This has the modern Haswell chipset. And these are small form factor servers. 10 of these 100 servers are going to be large form factor C240 series servers, again with the M4 chassis. What's going to be common across these two sets of servers is that each server will have two CPUs, each with 8 cores, running 0.4 gigahertz. And each server would have 128 gigabytes of RAM, and each of these servers would have one 480 gigabyte SSD drive installed in them. This is what is going to be common across these two sets of servers, but they differ in their rest of the storage configuration. The 90 small form factor servers will each have two about 1 terabyte hard drive, whereas the remaining 10 large form factor servers have much more storage in them. In particular, one 1 terabyte hard drive that Cisco is providing, in addition to 12 other 3 terabyte hard drives that Seagate has donated to our cluster. So there's a lot of storage in our cluster and a significant amount of network interconnect bandwidth, as you probably recall from the cluster diagram I showed a couple slides ago. So that was phase 1. This is kind of what's in that truck that I showed you a couple pictures like a slide ago. In the next phase, we would like to be able to add at least 140 additional servers that may be of these two kinds of categories, maybe not in the same proportion. There may be a difference in how we apportion these 140 servers across these two classes of machines. Like Rob mentioned, we also have plans to add a limited number of accelerators on some of these servers, in particular FPGAs and GPUs. This is something we have planned, and we are in conversation with people who build the net FPGA boards to be able to provision some of our servers with those cards. And again, the idea here is to be able to do interesting experiments with external accelerators on each of these servers. As opposed to the compute, which we are going to build out in two phases, with the second phase having more servers coming in, the networking is something that we have almost completely going to be building out in the first phase. Like I said, we have two sets of Cisco Nexus 3000 series switches, and the reason we picked these switches is for a variety of reasons actually. They both support OpenFlow 1.0, and we're going to be working with Cisco on building key OpenFlow 1.3 features into these switches as well. The chipset itself can support OpenFlow 1.3. In addition, these switches offer a variety of other interesting features. You can monitor instantaneous queue lengths on these switches at fine time scales. You can trace control plane actions, how routing protocols are updating fibs on these switches at fine time scales again. Each of these switches can support many different virtual instances per router, and there is support for a large number of routing protocols. So you could do your SDN experiments, also do a variety of other experiments with traditional distributed routing protocols or whatever other new distributed routing protocol is out there. Okay, so that's about a quick overview of our cluster in terms of how it is going to be built. I want to talk about the kind of experiments that we hope this cluster would support. So essentially what the cluster is going to allow you to do is achieve fairly low-level bare metal access to compute resources, to the underlying switching hardware. That, coupled with the fact that we have a very high bisection bandwidth and lots of storage and significant amount of memory, gives rise to interesting possibilities. You can do a variety of experiments that essentially try out disruptive ideas for stretching memory in a cloud, for exercising networking and storage resources in a cloud. And essentially, you could do a lot of interesting things at scale with this cluster. Let me give you a quick example of the kind of stuff you could do with this cluster. So for example, you could imagine building and trying out a variety of up and coming intra data center routing protocols. For example, Conga. This is a protocol that actually clumps together sets of packets into groups called flowlets and does switching of individual flowlets inside each switch so as to achieve high utilization of your network. Our cluster would allow you to try out an idea like Conga and essentially figure out how effectively Conga can enable end hosts to exercise the full 10 gigabit per second bandwidth that each end host is provisioned with. You could also use our system to try out interesting new transport protocols like data center TCP. This protocol, for example, requires monitoring instantaneous queue lengths so as to be able to modulate the sending rate of hosts. And because our switches support that feature, you should be able to do this and build on top of this protocol. You could also build interesting network virtualization technologies, where instead of just describing a logical topology, you could imagine building a system where tenants not only specify the logical topology, but also have actual physical constraints on, for example, the amount of bandwidth they would need for the links in their logical topology. And you could use a system to understand how scalably you can support multiple tenants within the underlying cloud infrastructure. That was on the networking front. In terms of memory, you could imagine using our system to try out a variety of interesting upcoming big data computational frameworks that do in-memory computation, things like Spark and Shark that people at Berkeley have developed, and try out new cloud scale resource management and scheduling systems such as Mesos and Tetris, which allocate resources. And the idea here is going to be that, of course, you could try out these things in a small cluster in your university, but essentially the scale of this would enable you to figure out applications scalably can these systems perform, help them work well. And then once you have these systems built up, you can imagine running interesting applications on top that leverage these networks. You could also use this cluster to build new models, for example, for cloud storage. Because we have a lot of memory and a bunch of SSDs and a bunch of hard drives, you could imagine trying out interesting ideas for tiered cloud storage. You could try out ideas for flat data center storage and software-defined storage that came about in SOSP and OSDI a couple of years ago, as well as new architectures for data center storage, such as just using main memory as opposed to any hard drives, so as to maintain persistent objects. So all of these things are examples of past research that you could imagine doing at scale and much more effectively using our cluster. Of course, a lot of other interesting possibilities that we are as yet unaware of are also easily enabled by this cluster. With that, I would like to hand off to Casey to speak about the Clemson cluster. Are we taking questions? Or?
Okay, so I'm Casey from Clemson. So we work with the Dell team. In this case, we work with the Dell research and also the Dell engineering. We had a lot of conversation already with the Dell, for example, the networking engineering team on what's their support for OpenFlow. So this is just kind of a representative picture on how the Clemson cluster is going to look like on the compute side. And then later on, I'll have an overall picture that shows what we see is the most interesting part is how the networking interconnect with these compute elements, and then also on the memory and the storage aspect to that. So I know that I screwed up on the order of the animation, so I'll just basically bring everything up. So the three main aspects here is really on the core count, not core count, but the way that they arrange all these number of cores in a very dense setup. So for every rack, we can hold 10 chassis. Every chassis, you are going to get 8 servers, and each server is a 20-core server. So this is using the latest 20-core chip from Intel, and that again through Dell, we were able to directly communicate with the Intel people to help enable that. So in this first set of nodes that we're going to bring up, this means around 20 or 2,000 cores, which means about a rack and a little bit more on the second rack. We also emphasize on the large memory. So you're going to have 256 gig RAM for every node. So with 20 core, that means around 10 to 12 meg RAM gig RAM that you can leverage for every core of computation. The baseline storage is going to be a 2 terabyte drive for every server, but we also have provisioned some of the very large memory or large storage nodes where you have 1 terabyte and 4 terabyte drives that's out there. So on the networking side, we have both InfiniBand and the Ethernet. So there's a lot of discussion on how do you transition HPC into a cloud world. So there's a lot of thinking that has already gone into how InfiniBand can be leveraged. So we don't want to just keep that out of the picture, but rather try to balance our investment on both the InfiniBand support and the gigabit Ethernet support. So we're going to have full bisectional bandwidth, InfiniBand support for all the nodes that we have, and then also we have the 10 and 1 gig Ethernet interfaces on each node. So this is the architecture that you're going to expect. So you have racks of these 10 chassis set up, and every server you're going to have the 10 gigabit interface going out. So every server have two 10 gigabit interface, but right now in the first build, we're going to build up 1 10 gigabit every node, and then at the same time, they're going to have the InfiniBand connection for every node. The InfiniBand connection will go directly to the InfiniBand chassis that will give you the full bisectional bandwidth. And then the Ethernet will go through the latest Dell switch. The top of rack switch is S6000. So if you look at Dell, this is S6000 is provisioned as a top of rack switch that supports OpenFlow 1.3. We actually work with them through several iterations, and we figure out this particular structure. So we're going to be all S6000 switches. So you have every top of rack, you're going to have the X6000, and then on top of it, we also use X6000, sort of like a core node. But one thing you are going to see is this is not full bisectional bandwidth. So through the Ethernet side, we had to make the pricing trade-off to fit into our budget. So you're going to get full bisection on the InfiniBand, and then you're going to get reasonably good bandwidth on the Ethernet. But then again, this is the first build. So based on the community feedback, once you start to do experiments, we would like to hear from you whether there's a need on expanding the Ethernet side of the network capacity, and we can work on that. So one thing I pointed out in the slide is this connects to the Clemson NextNet, which is a CCNIE network that is SDN enabled. We actually have our production team on the IT organization supporting that network. So even though it's not a hardware specification that will be listed specifically what those supports are, that basically means that if you have very specific network requirements, you need some SDN configuration beyond the data center connecting into Internet 2. We work very closely with Internet 2. We have been working on a lot of case studies with Internet 2. So we have a lot of leverage in terms of figuring out what is the right configuration for you to do off data center connections. So if you want to do 3-site experimentation, for example, with Clemson, Wisconsin, Utah, through Internet 2, we can make that happen, and then we can try to fine-tune it to meet your needs. So what are the experiments that we are sort of envisioning? So in addition to all the examples that Rob and Aditya already mentioned, so here we listed some of the additional things that we're thinking about. So one reason that we provisioned a very high per core memory, we wanted it to be able to deal with a lot of the large data computation. So one is media processing. If you want to do a lot of in-memory processing, Hadoop workflow or Hadoop-like computation, you have a lot of the needs of the per core memory. people are talking about on the networking side for network function virtualization, you actually have virtual machines that's hosting different network features. There, once you start to allocate these different virtual machines, you want every virtual machine to have reasonable access to memory. So if you want to experiment on the InfiniBand and Ethernet interactions, you can use them simultaneously. You can try to provision them different ways. For example, if you want to look at how you can have an application that have an MPI type of message passing support, and at the same time you use TCP/IP for external communication. Another aspect that sort of drive our discussion from day one is the cyber physical system aspect. So again, the computing and the storage and memory in the center can do a lot of real-time computation. And then through the network connectivity going out, you can connect to different physical instruments as needed. So we have a lot of discussion with the community, and we'd like to hear more from you this time. And again, bare metal control over the switches, 1.3 open flow, these are sort of the given expectation. And there, we can go a lot deeper in the finer grain details, what kind of support you need. So right now, Dell already had a beta code ready for the OpenFlow 1.3 on their switches. It's a subset of all the OpenFlow 1.3 that you can expect, but we have a list of that we can share as we move forward. Next January, that's when we expect the system to be up at Clemson. So at that time, we're going to have that information more accurate. All right.
So as you can see, what we've done is that's right. What we've done is built 3 clusters that are somewhat diverse. So depending on some of your experimental needs, like what kind of network topology you want to run on, or what you need as far as the cores or RAM or whatever, we can direct you to the right cluster. It also, by using a bunch of different vendors, it also ensures that when you do a measurement, you can actually, if you want, run it on multiple different clusters and make sure that you're measuring kind of something fundamental and not just a particular vendor's implementation of, say, OpenFlow. In addition to these 3 clusters that we've just described, CloubLab will be federated with Genie, which, for those of you who aren't familiar with the Genie infrastructure, it consists of a bunch of Genie racks. One of the main components of its infrastructure is a bunch of Genie racks. These are 50 very small clusters, around 100 cores or 200 cores, that are distributed on college campuses all across the country. So you can get some extreme geographic diversity with a little bit of processing and storage at each of those places. And these are also connected through Internet 2's programmable SDN-enabled network, so you can actually build SDNs between 50 different campus racks and the 3 big clusters that we just described, and run experiments that cross all of them. Genie also has a couple of other large clusters from existing projects like Emulab at several sites, and it also has some things that are a little bit more outside of what most people might think of as cloud, but the truth is that there's a whole lot of interest in tying in the cloud to things like wireless networks and mobile networks. So Genie includes some WiMAX networks. There are some LTE networks. We have an LTE network with LTE base stations and a programmable EPC core at Utah. And then beyond that, Genie federates with a number of international partners in Europe, in Brazil, in Japan, and a number of other places, and we expect to kind of leverage those existing federations to make those resources available to CloubLab users with the one account that you sign up for at CloubLab. We have a number of community outreach efforts. Through US Ignite, which is a nonprofit organization that connects people who have advanced applications with people who have advanced infrastructure. We have connections to a whole bunch of applications in areas of national priority like medicine and emergency response and smart grids. I mentioned that experimenters will have complete control over the resources that are given to them, and they won't be shared with anyone else at that time. But of course, sometimes you actually want to let in some kind of real workloads on your system, and so we're working with ACI Ref, Open Science Grid, and the HT Condor folks to have an optional opt-in kind of system where if you build your little cloud and you want to pound on your storage system or pound on your virtualization system with real jobs, you will be able to opt in and say, yeah, sure, let Open Science Grid schedule jobs on my cluster. Through Clemson, excuse me, they have a data intensive computing program that has a summer camp, and we're also working with a few underrepresented groups at Navajo Technical University and University of Arkansas at Pine Bluff. So I want to jump away from my slides for a minute here and give you, earlier I said that, I wanted to make it as easy to get an entire cloud as it is to get a virtual machine. So let me see if the network will cooperate. Let's see. Okay, so I'm going to go ahead and log into my account at cloudlab.us. I'm going to go through this pretty quickly so that I don't run over. And I'm going to start a new experiment. And I mentioned that CloudLab is built around this idea of profiles. So we have some profiles that we as a facility provide that have, boy, it's pretty hard to read, sorry about that. That we as a facility provide that will include standard cloud software stacks that we think a whole lot of people are going to want to use. So for example, I'm going to pick this one here. This is OpenStack running on the ARM64 machines, that cluster that I showed you a picture of at Utah. And it's got a few compute nodes in it, a controller, a node manager, and it's a network manager, and they're all connected to this 10 gig network. And I'm going to go ahead and pick that profile. I actually get to select which of those clusters I want to run it on. At the moment, we support running on one cluster at a time, but that's more a user interface issue actually than all the technical stuff is in place underneath. But so this one's I'm going to run at the Utah CloudLab cluster, and when I click create, it's going to start configuring some of those machines into the topology that I just asked for, loading disk images, getting OpenStack configured. And so this will take about 5 minutes or so. So I'll finish up my talk and then we'll come back and we'll see if it worked. So let's see. And now I lost my external display. Oh, excellent, good. And this so let's see. So now I have, okay, so now I get to skip through all of the slides that were what if the network doesn't work. That's a good feeling. So while that's getting created, I wanted to talk just briefly. We expect that a lot of people will start with the profiles that we provide, right? They might start with the standard installation of OpenStack, and they might start with something that's just a set of N bare metal machines with a standard operating system on them. But of course, what you're going to want to do is you're going to want to actually build up your own stacks and build up your own profiles, so you can share them with your colleagues and publish them. Something become really slow, but one simple way to do this is to take an existing profile. What I can do is I can take a profile that is provided by the facility, instantiate it, log in, get the disk image the way get the contents of the disk the way I want by installing packages, upgrading the kernel, whatever it is I want to do, and then I've got this clone button that'll make me my own copy of that, and then I can send somebody like a link to it, and when they follow that link, what's going to happen is they're going to get their own instantiation of that profile. So they get their own resources. They get the same environment as me, but actually on a separate set of hardware, so that we're not interfering with each other. We also have a GUI that we developed that we're developing as part of the Genie project. This is called JAX. So this is good for building small to medium size experiments. So you get to a palette, and you can drag nodes out on it and connect them and select them and set operating systems and node types. And this is intended to be a nice, simple, user-friendly interface. It actually knows enough about the clusters that the topologies are for, that it helps you it helps make sure that the thing that you draw can actually be instantiated on the hardware that we have. Of course, if you want to run something really big, like say building something that you really might call a cloud, dragging and dropping nodes on a GUI is not, going to get you there. So this is something that's in alpha right now, but basically we're using a library that was developed for the Genie project called GenieLib that is built for manipulating the topology and resource descriptions. So essentially what you can do is you can actually write, Python code to, create machines, connect them together. So, you can write a loop that says, for 1 to 300, add a new node, set its operating system, put it in my 10 gig LAN. And then finally, you can actually build these things like entirely from scratch if you want. The profile is defined using a Genie resource representation called an RSpec, and it's an XML representation. And thank goodness I don't have to keep showing these to people anymore because we have the nice tools that go on top of it. But if you want to edit or generate these things yourself, you also anything you can do to generate an RSpec, you can upload it. So a word about availability: we've had what we call a technology preview up since August, which has let we've actually had some people, I think a few of them are here, actually doing some actual real work on our technology preview. It's available for use now. For brave users, you can come sign up and use it as it is now, and then over the next months and years, we'll be refining it, etc. So this picture was the best thing I could find, I think, is a metaphor for what it would be like to use CloubLab right now. So I don't know if you can tell what's going on, but there's a locomotive in the back, and the guys are in front of it are like laying the rails, right? So if you come use it now, we'll literally be laying the rails in front of you. We're adding features to it every day. Like I said, if you're brave, come use it now, and this gives you a chance to help steer where we build those rails. Or if you want to wait a few months until the frontier of rail building is farther out from the station, that's good too, right? So if you want to sign up, you go to cloublab.us. If you click the login button, there is a sign up link on the page that comes up. This is basically the whole form to start a new project. And then one last thing before I go back to see if my experiment worked. Is I just wanted to introduce you to, this is the CloubLab leadership team. There are actually a whole bunch of other people also doing kind of a lot of the day-to-day work on it that I didn't fit onto the slide, but I just want to introduce the people who are here so you can recognize them. So I'm Rob Ricci, I'm the PI at Utah. Also from Utah, my colleague Eric Eide, who's over here. And Eric is interested in repeatable experimentation in middleware and programming languages. From Wisconsin, you met our PI there, Aditya. We also have Remzi Apache Dussault, who's over there in the back, and he does a lot of work on storage and operating systems. From Clemson, you met KC, and Amy, who you heard about earlier, going to NSF, does like a lot of systems work that is involved in data intensive and computing and HPC, and is also interested in the educational aspects of this. From BBN, we have Larry Landweber, who is a consultant at BBN and actually also emeritus at Wisconsin, has been building this kind of stuff for a very long time. From UMass, we have Mike Zink, who works with cyber physical systems, and his team is going to be the one doing some of the instrumentation for getting power data and environmental sensors back to users. And then from US Ignite, we have Glenn Reichert over here. And Glenn is the guy who knows all the applications people and all the infrastructure people. And then, as I've mentioned before, we have our three partners, hardware partners, HP, Cisco, and Dell. So now let's see what we got. Oh, it got stuck. So you can tell it's a real demo. So I have to go take out the cake that I baked last night. Let's see. So you can see I actually have like 8 clouds running right now. In the oh, maybe the network's just not. Maybe yeah. Okay. All right. So I won't show you the OpenStack interface, but. So go ahead and sign up for an account at cloublab.us. The truth is, actually, if you already have a Genie account or an Emulab account, you can just use that account to log in. You don't even have to actually sign up for a new one. All right, thank you, and I'll hand it over to Kate to talk about Chameleon.